Okay, thank you. So this is joint work with Mariam Barani, who is at A16Z Crypto. Okay, so let me start with just kind of like the starting point for this. So this is a talk about consensus mechanisms, not about violating consensus, but about manipulating consensus algorithms. So when I first got into this space, maybe like seven or 8 years ago, the classic view was the dominant view, which kind of said that blockchains are protocols, honest participants follow the protocols, malicious people don't. And these are things like if you've heard of double spends or network partitioning or double signing or stuff like this was the thing that everyone thought about. And a representative goal was you said, well, if the attacker doesn't have that much hash rate, stake, whatever, then you get some desirable outcome. Now, I think the thinking has shifted a little bit, not to get away from the security view, but to just add a mechanism design view, which is if blockchain protocols are really games, the participants are strategic, they're trying to optimize their payoff. And a representative attack to consider here would be like selfish mining or timestamp or randomness manipulation. And a representative goal here would be to say that if the attacker is not particularly large, then it's a Nash equilibrium for everyone to follow the protocol. Both of these views are definitely important. I tend to think that they're best studied kind of separately, that you want to separately show your protocol satisfies view one and separately show that it satisfies view two. And as far as I know, both of them are well represented at this point in discussions about consensus protocol now. Okay, however, my background, I'm going to focus, everything I talk about is exclusively about the mechanism design view. And what's been happening, since the V paper that started this is the selfish mining paper from 2014. And then there's kind of been a ton of work since then showing all these different ways in which a lot of the popular protocols are not in equilibrium. So, for example, there's the seminal selfish mining strategy is strictly profitable in Bitcoin as long as you have sufficient hash rate. Probably there's no single miner who has, anywhere close to 32.9% of the hash rate, but there are other conditions under which it would be profitable. There's a nice recent paper about timestamp manipulation in Ethereum, and then also on manipulating random seeds and BFT protocols. And what I'd maybe point out about the bottom two is that any participant could do those. So you don't need to be large to profit by manipulating seeds. This holds in Ethereum too. And there's so many different kinds of attacks of this form. Okay, so that's sort of like, as I'm generally a theorist. As a theorist, we say that's pretty cool. So there's all these conditions under which players can strictly profit by deviating from existing consensus protocols. And then overwhelmingly, nobody is doing this. And there's one exception. That's actually from a paper of Aviv, who was the first speaker in this session. That is the only exception I know of where anyone has done any of these profitable manipulations in practice. There's a little asterisk, which is I don't know how hard people are looking for this. I'm quite confident that nothing has been detected, but it could be that stuff is going on and it just took, people just aren't looking the right way to find it. But I am confident that nothing is being detected. Okay, so as a theorist, the next thing I want to think about is like, how could this possibly be the case? So is it just that people don't want free money? I don't think that's the case in the blockchain space. Everyone seems to like free money. And I just want to provide more context for this, that these deviations are not traceable. So you have this, pseudonymous system. If a pseudonymous person decides to deviate from a protocol, because the system is pseudonymous, you can't, go and throw them in jail or something like that, right? So you'll never know who did it. A lot of these, I'll emphasize, a lot of these deviations, they're profitable no matter how poorly connected you are to the network and no matter how little stake or hash rate or whatever you have. So it's not that you need to have all this computational power that people don't have to profit. There are people who can do it. And also, even for these simple ones like selfish mining, yes, I don't think anyone can do it on Bitcoin, but definitely single entities have controlled enough hash rate on an altcoin to do it. And also, it's still not been detected. So if there's interest during the Q&A period, I can tell you more context for all the different reasons why this may not be happening. However, I think there's a single convincing argument that kind of like is not specific to different points in time that says the following. So all these deviations, if you work out the math, you say, why is it profitable? Well, it's profitable to selfish mine on Bitcoin because it gets you more Bitcoin. It's profitable to manipulate timestamps in Ethereum because it gets you more ETH. All of these deviations, while I can't trace to figure out exactly who did it, all of them are definitely detectable. So I'll go through for selfish mining exactly why, how you would detect it. But you would look at the Bitcoin blockchain and you would say, something doesn't look right. Something about this is wrong. And what you would be concerned about is that maybe if it becomes public knowledge that someone is trying to manipulate something in the Bitcoin blockchain or Ethereum or whatever altcoin, you might be concerned that all of a sudden this 1% extra Bitcoin you got is worth like significantly less USD. And so yeah, it's cool, you manipulated something, but ultimately you lost a bunch of money by doing so. Okay, so I find this argument fairly convincing. It applies in a lot of different settings. And again, if there's interest after the talk, I can go through different arguments and try and contextualize where they make sense and where they don't. Okay, so what's the point of this paper? So I find this to be the most convincing reason why nobody is doing this stuff in practice and why they may never want to do it in practice. And so what we tried to look at is, well, is it possible to somehow get around this argument and maybe do a profitable deviation from, we looked specifically at Bitcoin, in a way that is not detectable? So the main result here is yes, it is possible to do that. And let me elaborate a little bit on what that means. I'll get into a more precise statement in a bit. So what is this saying? This is saying that you do need to be a large miner. So I would still say this, I don't think, now that the paper is out there, I don't think someone's going to all of a sudden say, oh man, I have 40% of the Bitcoin hash rate, I'm going to go ahead and do that. This is huge. Nobody has this. But if you were this large, then what you could do is you can do something that is strictly profitable. So I'll overview why this is the right measure to use for strictly profit. And you do it in a way so that the pattern of orphan blocks that you create is fully consistent with there just being a little bit more underlying latency. So what that means is that as an onlooker, you would look and you would just say, okay, I guess there's some latency. And there is some latency. And you'd have no way of knowing whether the latency is caused by things that normally cause latency or whether it's caused by someone being strategic. But you can strictly profit. You can manipulate the underlying consensus protocol in a way that nobody would be able to tell that it's any different than routine latency. Okay. So what I'm going to do in the rest of the talk, I am going to give a very brief overview of this. So I think this will probably not be enough to teach you the attack if you've never seen it before, but maybe just enough to understand, why is it detectable and how might you get around that. And I'll get into a more formal statement. And I'm pretty sure I'm going to skip this, but I'll tell you kind of what I think. And again, maybe I'll just try and overview some of the arguments, other arguments for why people don't do this at the end. Okay, so probably everyone has seen some picture that looks like this. So this is a blockchain. So these are blocks. Every block points to something previously. And it all points in time. So what is the game induced, by the Bitcoin protocol is that whenever you create a block, you get to decide where to point. So there's a recommendation that says, please point to a specific block called the longest chain, but ultimately you set that as your mining. You choose wherever you want to point. And the other thing you choose is you choose whether and when to broadcast your blocks. So just repeat, so what the Bitcoin protocol, what the longest chain protocol asks people to do is it says, this is the longest chain, please point here. And that's what it would like you to do. You are free to point here, you're free to point wherever you want, but it asks you please point here. And it also says, as soon as you have successfully proved work, so this is saying, as soon as the hash of the block you create is small, please just broadcast it immediately. So there's no way to enforce that, but it asks you to please do that. Okay, and so let me maybe go through this a little bit quickly, but if you want to ask me about why this is the case, I'm happy to take a question on that. But I basically just want to state that really the right reward to consider in this game is you want to maximize your fraction of blocks in the longest chain. So you don't want to just maximize the number of blocks you have in the longest chain or something else like that. You really want to maximize the fraction of the longest chain that is created by you. This is a brief justification for that, and I'm happy to take questions about that, but I'll skip through this for now. Okay, so what is the game? The game is when you create a block, you choose where to point and you choose when to broadcast. So what does longest chain say to do? It just says, please point to the longest chain, please broadcast immediately. So that's what an honest person in the Bitcoin network would do. Okay, and then what are the rewards you get? It's proportional to the fraction of the longest chain that are created by you. All right, and so then the key question, like I mentioned, is when is it a Nash equilibrium for all players to follow the longest chain? So this is the result from Ayala and Sierra, their selfish mining strategy. And so what they propose to do is the following. They say, actually still point to the longest chain. So they're not really going to be violating consensus. It's not a consensus breaking attack. And the only thing they ask to do differently is, this is sometimes called a block withholding attack. So they say, when you find a block, do not immediately tell everyone else about it. What you should do instead is, if there's a real risk that your block might not become the longest chain, you should broadcast. The other thing you should do is, if your block is the one that's going to like decide what is the longest chain, then you should also broadcast it. So I'll show you a quick picture on the next slide to go through this. So basically what the strategy does is say that, you know, the honest party finds a block here. You find this next block, you should not broadcast it. So there is currently no threat to this block that this is the unique longest chain. There is no rush for you to broadcast it. If you find another block, you will point to it because you know that this is the longest chain, and you are also going to hide it. You're going to wait. If you find another block, you get very lucky, you're going to also hide this one. So now when would you start broadcasting? So someone else is going to find a block. They can't point to yours because you haven't broadcasted. They don't know. So they're going to point to the longest chain that was previously broadcast. At this point, you look at this guy and you say, oh my gosh, there's another block of the same distance to the root. I should broadcast because now that block is in danger. However, you still know that actually things are very safe. You have a lead of 2. You have some time before anyone can actually create a longer chain than yours. So now someone else creates another block of height 3, and that's going to trigger you to broadcast this one. And now you also realize you're like, okay, this is a little bit scary. I have my lead right now. This is the last time I'm guaranteed that I definitely have the longest chain. And if I wait, then maybe it'll be tied. I'm not sure how everyone else breaks ties. I'm nervous about that. So I should also just broadcast this. So this is what the selfish mining strategy does. And these guys showed, oh, sorry. And then what happens is after you broadcast it, now everyone's going to tie break in favor of you because this is the unique longest chain. Okay, so what am I going through here? So, okay, so what I want to point out is that this strategy, it's not risk-free, right? So another thing that could happen is you hide this, they find this, you broadcast the match. If you find the next one, then you're like, okay, that was lucky. I got my blocks in, I got my 2 in, I kicked out one of theirs, that's good. You could also get unlucky and you could not find the next one. And if you don't find the next one, then you lost this block and you have less blocks in the longest chain. So to actually figure out whether this is a good idea, you need to outweigh, you know, the benefit of when you find a lot of blocks versus the cost of when this happens. Okay, but they did the math and they showed that if you have at least a third, it's profitable. Yeah.
Quick question. The reason why you don't want to reveal right away is because you want to maintain the largest fraction yourself.
Exactly.
Right? Okay.
That's exactly right.
Worry that other people might join the chain.
That's exactly right. So if all I wanted to do was to maintain the largest number, this would serve no purpose. That just being honest is best. All my stuff will get in. That's great. But it's specifically because I am trying to get the largest fraction. I do want to kick other people out. That's right.
Great.
The first block would be would broadcast it if even if it was so with that one, how do you know? Where are you going to bring it again?
Yeah, so I think my language was maybe a little bit sloppy. So I would say here, this is I'm deciding to take a risk. So when I hide this first one, I'm explicitly deciding I may lose, but I want to give it a shot anyway. That's the only point in this strategy where I take a risk. from then on, I just say, if I can win, I win.
Yeah. So I'm wondering, like, the reason that you want to optimize the proportion of your block is like, so in this case, I think the total number of the block will reduce, but is the reason that maybe after some time the difficulty will change.
That's exactly
So
correct.
you're gonna get more profit.
That's exactly correct. Yeah. So basically, it's because of the difficulty adjustment, the time average reward. If you cause there to be less total blocks in the longest chain, then the difficulty becomes easier, and so your blocks become you can create blocks at a higher rate. That's exactly right. Okay. Okay. So they showed this. It is strictly profitable as long as you're bigger than a third. There's a follow-up paper that showed a slightly more clever one that's strictly profitable as long as you're above like 32.9%. So now I want to talk about how would I try and detect that someone is doing something fishy. So I want to ask, if you look at this picture, what looks weird about this compared to the situation when everyone is honest? So one thing you might initially think is that this looks weird because there are conflicting blocks. And I would say that's not what's weird. This does happen sometimes due to latency. So I did learn that this is very uncommon, at least a year ago in Bitcoin that this happened, but it does happen. And you could not single out just because there's an orphan, somebody must be manipulating something. It does happen sometimes. And in particular, the blocks are found by this like independent stochastic process. You basically have like different Poisson clocks and they might tick near the same time. If they tick near the same time, then they won't know about each other and this will happen. I think what's weird about this is the pattern of orphans. So in particular, if the orphans were really because of latency, then you would say, you know, just because two Poisson clocks happened to tick near the same time 10 minutes ago, that doesn't make them any more likely to tick at the same time, you know, the next time. Everything is independent from block to block. However, if someone is selfish mining, the fact that you have some orphan block here, that makes you much more likely to have an orphan block in the next time step too. So in particular, what you are much more likely to see is runs of orphans compared to just the raw number of orphans. So proportionally, most of the orphans will appear in long runs. So that's what's odd about this. Okay, so then the point of the paper is basically just to say, is it possible to be strictly profitable to do something like selfish mining in a way that still makes the orphan pattern look like independent? So what am I trying to finish? 8 minutes. Oh, okay. So, all right. So here's what we consider. We say there's two players. One of them is the attacker. They're going to try to selfish mine. The other one is honest. They're just following the longest chain protocol. And in each round, either one or both players finds a block. This is independent of everything that happened previously. This is what would happen with natural latency. And so what do I mean? There is some natural latency. So with some probability B, they both find a block, or, you know, just honest finds a block, or just the attacker finds a block. Okay, and so now what we observe is in this model, if both players followed the longest chain protocol, then each height would have an orphan independently with probability B. And that's just because the only reason you would have an orphan is if this event happened, this event is independent across rounds. So what does the attacker want to do? So they assume that the honest party is following the longest chain. We're just trying to establish whether it's a Nash equilibrium. We're not trying to like optimize or find the Nash equilibrium. We're just trying to see whether it is a Nash equilibrium, to be honest, and we're trying to show that it's not. So the attacker, I would say it's strictly profitable if they get a strictly bigger than alpha fraction of stuff in the longest chain. And I would say it's undetectable if the pattern of orphans is such that every height has an orphan independently with some probability. So they can't match exactly the underlying latency, but nobody really knows exactly the underlying latency anyway. And I'll also ask for this even stronger property that I'll say if it's the case that for every epsilon bigger than 0, there is a strictly profitable, undetectable strategy getting you kind of like arbitrarily close to the natural latency. So what I mean by that is maybe you don't want a strategy that like all of a sudden doubles the rate of orphans, that maybe you would say, okay, someone will probably detect that and that makes me scared. But if you can get as close to the natural latency as you want and still be strictly profitable, there's probably some range in there that you'd be comfortable doing. And okay, and so the main result is basically that, yes, there are strictly profitable, undetectable deviations that get you, as long as you have at least this much hash rate. Okay, and I think I will take a couple minutes to go through this and basically just try and say like what's the like what's like a one thing you have to consider when thinking through this. So, like we discussed, this is kind of like the good case. You get this lead, and now someone's caught up to you. And what the selfish mining strategy says to do is hide this, definitely create an orphan. And if you do that, then, this means that you are way more likely to have an orphan at height 2, given that you had an orphan at height 1, that's going to be detectable. So you don't want to do that. What's another thing you can do? You could say, the moment this happens, just immediately broadcast both. You could do that. That would still be profitable. Now the problem is you're less likely to have an orphan at height 2, given that you had something at height 1. Okay, so basically you want to say, okay, this doesn't seem so hard yet, that maybe what you should do is you should like flip a coin to decide whether you auto broadcast the second block or not. That seems like a good place to start. And I would say basically the challenge is twofold. So one is if you're in this situation, you really want to broadcast this block the moment you find it. You do not want to be risking creating an orphan here because you really want to win. If you try to create an orphan here, you might lose. So this means you can't just, you can't just go back here and say like, well, what's the probability that you're here? Like you can't just say like, oh, I'm trying to induce a certain probability. Let's see, what I get when I do deterministically this. What do I get when I do deterministically the other? Let's see what I get. Because I have to take into account the fact that if I wind up in this situation, I really want to broadcast with probability 1. The other thing that might happen is if this happens, then there's also definitely not an orphan at height 2. And the other thing that might happen is, where is it? The other thing that might happen is just like these orphans happen on their own sometimes. So that's another thing that might happen. So basically the main trick here is you do have to be quite careful figuring out all the things you really want to do in order to be profitable, all the things you can't control, but it is possible to get this to work out. The harder question is figuring out what is actually the fraction of blocks you have in the longest chain. I'm not going to give any intuition for that, but that is possible. Okay, so let me give a conclusion slide, and then maybe I will pause for questions. And if there's not a lot of questions, I will briefly describe some of the other justifications that are out there for why people aren't selfish mining in practice. So the motivation for this talk is just that in practice, according to the theory, people could be strictly profiting by manipulating consensus protocols. And overwhelmingly, people seem to not be doing it. And I argue that I think, in my opinion, the most convincing argument is just that you don't want to be detected. Even if it can't be traced back to you, you probably don't want to risk tanking the value of the crypto asset you're manipulating. And so what we showed is that, at least in the simple Bitcoin model, it is possible to, so again, you can compare this to maybe the 32.9% you need to profitably manipulate it all. This is bigger, but it's not that much bigger. So it's saying that if you want to manipulate it undetectably, you can do it if you're a little bit more powerful. Okay, and then so where am I hoping this will go in the future? So if you're maybe a very technically minded person, I would say our strategy matches a specific orphan pattern. That seemed natural to us. If you're much more into modeling network latency, maybe a different model is what you would actually expect the natural orphan pattern to look like. A second thing is if you're kind of like much more thinking about like, if I were to actually run this attack, what are other ways I might be detected? The main thing I would think of is that there is timestamp information in every block. manipulating the timestamps to look like natural latency is, I think, a harder question. I don't know whether I think that would be possible or impossible. The other question I would want to ask is just like, if the exchange rate of Bitcoin depends on the timestamps in the blocks, like what would that mean? Because like the timestamps play no role in consensus. They intentionally play no role in consensus. There's, this previous paper I didn't mention is that when they do play a role in consensus, because they're so easy to manipulate, that's really bad. So I don't really know how to think about this question, but I think that's maybe like a one thing left open. And I would say the broader question is just that this argument, where is it? This one, this is used a lot. So this is like, it was in, I think, even, Nakamoto's original white paper. It's really, really widely used as a reason for like, come on, you don't have to worry about mechanism design. You don't have to worry about attacks. Nobody's going to do this stuff. So if they do it, they're just hurting themselves. And, I do buy that, but I think that there's maybe an over-reliance on that argument. And I think that thinking through stuff like this is, I think, a good step to understanding the strength of that argument. Yeah, and I would say the last thing I would say, theory has been, I don't know if predicted is the right word, but like if you take theory literally, theory has been predicting something would happen in practice. It hasn't happened. And I think it's good for theory to try and understand why we're not matching practice. It's good for practice to understand, why things are happening and when theory is useful. Okay, so that's all I have. Thank you. I don't know who's picking the questions, but.
Okay, so thanks a lot for that. So first one comment and then a question. So you say that nowadays orphans are quite rare, typically of forks are of depth 1, but just to give credit to the original paper back in 2013, 2015, forks of depth 2 were happening every day or twice a day, and depth 3 a couple of times a week. So you could have done this without detection. Now the question is, in your example, why wouldn't the attacker release all 3 blocks at the site of the first longer chain block? Wouldn't that be the optimal?
You mean back? So you mean when I had?
Yes.
Like here.
3. And then this one appears. Why wouldn't I just release all?
Yeah, so it's better for me to knock out 2 of theirs. So think of it as like every block of someone else that I knock out is good for me because I'm trying to get greatest fraction. If I just, so like having this lead means that if you find the next block, that's wasted. So being in a state where the next block you find is going to be wasted is better for me than immediately going to a state where the next block you find would be in the longest chain.
Well, if it's just one time, but because it may be detected, there is a risk, right? So
that's exactly right. Yeah. So that's exactly right. So balancing those is exactly the game of the paper. That's correct.
Isn't there a second order? The argument for why it doesn't happen is that even if you do succeed, you might have a hard time selling the coins. So there's the value dropping argument. There's also the fact that if the community responds strongly enough, exchanges and other places might either refuse to accept the deposit or dox you.
So I think in order to do that, it would need to be detectable. And it would need to be traceable. And just like if I showed you this picture, like say that I make a different public key.
Yeah.
I make a different wallet for everyone. And I show you this picture, you're gonna refuse both of these. Like every time I create an orphan, you just say those coins are no good here. And like I definitely agree that if it's traceable back to me, I would be terrified of like what either combination of the US government and other forces would do to me. But if the whole point is it's a pseudonymous system, and if I really think that I have some pseudonymity, then it couldn't be traced to me unless you want to just like target everyone who has a orphan block.
Okay. And to that point, does all else equal, do block times matter just because faster block time proof of work chains have a higher orphan rate?
Yeah, so if you're asking like are you asking sort of like what Nakamoto consensus protocols would be more or less vulnerable?
Yeah, like Litecoin
Yeah.
versus Bitcoin for
Yeah, so I would say yes, I think that's roughly the right way to think of it. That like sort of like in if in Bitcoin, if like for example, I think you were the one who told me that the natural orphan rate in Bitcoin at the time we last spoke was ridiculously low. And so if you think Bitcoin would look weird just because there's like an orphan a day, that just limits the amount you can possibly do this to profit. Whereas if other ones look weird, if other ones would look normal with like thousands of orphans a day, then that opens up more opportunity to profit here. Yeah.
One quick question on this. So for here, actually, what you could do is if you're trying to show that someone's selfish mining, you could like release the second you release a block, you release a bunch of like high value transactions, right? That you would be sure would be included in a kind of like honest protocol. And so, you could say, oh, the network delays are too large, but the point is you're trying to make it roughly so that the timestamps line up somewhat naturally. So I don't know, is this like a quasi mitigation for someone trying to pin you down on this?
That's an interesting question. I need to think a little bit more, but I will do that right now and then talk with you right now.
Thanks.
All right, well, let's thank the speaker again.